Okay, so welcome to the third part of lecture 17. We're going to cover the second topic of this lecture, and that is the topic of thin film interference, which is covered in section 24.4 of Survey 11th edition. Our simple single objective here is to understand how interference can occur when light reflects from the two surfaces of thin film. Okay, well, what is the definition of a thin film? Right, so let's get that out of the way. So a thin film is a coating or fluid that is on top of another material and has a thickness defined as T. And that thickness is on the order of the wavelength of light. Okay, so a material slash coating on top of another material that has a small thickness defined as T and on the order of lambda, right? So it has to be within a factor of 10 of lambda. And thin films, well, maybe 10, 30, right? Thin films cause overlapping of two reflected rays. So thin films cause, I'm going to use a more technical term here, cause superposition. Remember that from Introduction to Waves. And if you haven't seen waves, don't remember waves much, please review that or ask me questions about it. So thin films cause superposition of two reflected rays. Okay, and rays again are just that's just our idea of visualizing it as rays. All right, and let me draw a little picture to do just that, to visualize it. So let's draw the thin film. Okay, so let's do that in red. Let's kind of set some colors here for that. So this will represent my thin film. Okay, underneath the thin film will be some other substance. I'm just going to call that, I'll represent it with some highlighted color, something like this. This is just our underneath substance, for example, glass or something. Okay. Yeah, okay. Right. Green glass, sure. Okay, and so there we go. Let's label some things here. So this will be the substance. For example, n equals 1.5. Okay, this will be the film up here. Right, this is the thin part. And this one will have an n of, we'll say 1.3. Okay, and then we got air up above, which is just going to be our n of 1. And here's the idea. We're interested in light that's coming in at an angle that's fairly parallel to the normal. But we don't want it to be exactly parallel to the normal, but we want it to be, kind of somewhat parallel to the normal. So it really works for light that is fairly orthogonal or fairly perpendicular to the surface. And when it comes in, it does something like this. Let's draw a ray kind of coming in to think about what happens. Let's have a blue ray. Something like that. Okay, so here's our ray coming in. It's going to come down to the thin film. It will, of course, get refracted, and it's going to get refracted towards the normal, so it'll be kind of steep down there. And then it will get refracted further towards the normal as it moves into, in this case, as it moves into the next substance. However, refraction isn't all that happens. There's reflection at the first interface between the air and the film. So there's some light that gets reflected, and of course it will get reflected at the same angle that it came in at relative to the normal. Okay, and then at the next interface, the interface between the film and the substance, there's going to be further reflection as well as the refraction I already drew. Okay, so that would look something like this. So the idea is that the film is so thin that these two reflected rays, okay, so these are the two reflected rays that I referred to. The two reflected rays. These two rays overlap. They're close enough to each other that they actually interfere with each other. And in the same way that double slit interference can result in constructive and destructive interference, these two overlapping, superimposed waves, represented by rays, can interfere with each other. And in fact, if we think about the wave that exists visualized within that ray, it would look something like this. Right? I'm zoom in a bit on it. So let's imagine the first wave coming in. Okay, so I have it kind of enter exactly like this. Almost. Just wasn't quite happy with the drawing. There we go. Okay, so something like that, right? That's our original incident ray. So when that ray gets reflected, it's going to get reflected potentially with a phase change. Okay, so we have to think about kind of when that phase change can occur. And there ends up being a half wavelength, pi radian, 180 degree phase shift upon reflection whenever the index of refraction of the next substance is higher than the index of refraction of the prior substance. All right? So, for example, going from air into film, because your film is always going to have a higher index of refraction than air, because air is as low as it gets, that's going to be an increase. And that means that the reflected ray has to be out of phase, right? It has to be exactly out of phase. So if it came in as a trough, right, because that's what we're seeing here, right? The wave, if we think of this half wave as being a trough, the reflected ray would have to come out as a crest. Okay, so it would look like this. And I'll write this in the key terms in just a minute because it's kind of the rule here. Okay, so that would be the reflected ray occurring at that interface. So it actually means that those two rays, if the light was exactly incident, that they would cancel each other out, right? So that particular reflected ray would cause for no reflection, right? We essentially have a case where we wouldn't be getting an image, right? We wouldn't see anything coming out. All right. So that's why if you just have a single substance, you're not able to see yourself in it, right? If you think of just like holding up a sheet of plastic, you don't see your image in that sheet of plastic, right? You need something to cause that image to get created. You may be like, well, I see my reflection in the window all the time, Well, that's because there's two interfaces, right? There's an interface between the air and the window, and then again another interface between the window and the air. And that's the whole idea of the thin film, okay? All right, so let's think about what's going to happen then. So then the refracted ray / wave that continues into the film, that one doesn't have any phase shift. Okay, so that one's just going to continue on its merry way, have something like that. Its wavelength would change. In fact, its wavelength would become smaller because we're dividing by the index of refraction, and I indeed drew it with the smaller wavelength and smaller amplitude because some of the energy would get absorbed. But then what's going to happen, right? Well, now at this next interface, we're going to go from 1.3 to 1.5. Well, is that going to cause another phase shift? Well, yes, it absolutely will. Okay? So again, if it's going to be entering as a trough, then it's going to get reflected as a crest. So now, these two reflected rays, with their wave properties shown, right, even highlighted, right, with these two reflected rays, we see that because of the two occurrences of phase shift reflection, right, because in both cases we had a complete 180 degree half wavelength, pi radian, phase shift in terms of the reflected rays, that the overall effect of that meant that when the two reflected rays came back together, they ended up being in phase with each other. Well, that's interesting. It's because now that light is going to constructively interfere. It's going to create basically a effect, like a reflection, right? You will see light coming back out. Maybe we could see an image. Maybe we could just see, kind of like a hue of light, a glow of light, right? But there would be light coming back out that the eye would be able to pick up or a sensor would be able to absorb. So that's light that is constructively interfering. And maybe that light would be actually, kind of existing in the same space, whereas maybe those rays would not be overlapping with this ray. Because you'd imagine that if you had light that was much more with a much larger angle relative to the normal, well, that light is going to get, get refracted in, and then it's going to end up with two beams coming out, and those two reflected beams would overlap essentially, because we'd have a very small deviation in terms of their angle, but they would be very far away from the original incident beam. And so there wouldn't be a chance for the incident beam to destructively interfere with either of the reflected beams. And so then all you would get is in-phase bright light being reflected. Okay? So what's all the takeaway of this, okay? Well, the takeaway is that you have a case in this particular instance, in the diagram that I drew, where you went from lower to higher in terms of the index of refraction. It just kept going up. And because of that, we had those two occurrences of phase shifts upon reflection, okay? But before I continue, let me write that in our key terms. All right. All right, and we'll wrap up this video as soon as we do the key terms and then identify the formulas, and we'll save the examples for our fourth video. Okay, so key term here, though, is reflective phase shift. Okay, so the reflective phase shift can be summarized like this. Okay, so first of all, conceptually, it is just the phase change of exactly pi radians that is possible with reflection. So it is the phase shift of light of exactly pi radians, which is equivalent to 180 degrees, which is equivalent to half a wavelength, right? Because that's three ways of saying the same thing. And make sure that makes sense, that is three ways of saying the same thing, because that right there is the key to all of this making sense. Everything we talk about waves is so dependent on making sure that you kind of have that understanding about, what does it mean to have phase shifts and sine functions and the whole oscillatory nature of them, that they repeat themselves, and they repeat themselves every 360 degrees, / every 2 pi radians, / every full wavelength. You could say also every full period, right? Okay. So exactly pi radians, et cetera, that is possible upon reflection. Okay, so if NB, so that's the second one, right, is higher than NA, A comes first, B comes second, then there is a reflective phase change. Okay, so that would be the case that I drew above. Okay, however, if NB is less than NA, then there is not. Okay, there we are. So what does that mean? Well, that would be a case of going from a film like a bubble, right, a very thin bubble, air, bubble, air, right? So you'd have air to bubble would be higher or lower to higher, so that would have the reflective phase change. But then when the light exits the bubble back into the air on the other side of the bubble, other side of the soap film, then you'd be going from soap film to air, which would be a NB that's lower than NA, which means no reflective phase change. Excuse me. And so in that case, you would only have one case, right, where you'd have the reflective phase change. And so then one of those, right, so if this was like back to N1, then the reflected ray would look like that instead, right? It would be a trough, just like incident was a trough. And so then it would look something like this. So then when that one came out, it could potentially be destructive with the other reflective ray. Now that's interesting, isn't it? Because now you got a case where that thin film can lead to destructive interference. So if you want light to be canceled out by films, if you want a, say, reflective protective coating on your glasses, you have to make sure that that material is made out of an index of refraction that's higher than the glass. So if you had a glass of 1.5, then your film better be higher than 1.5. Better not be 1.3, would it, right? Because then you're never going to get destructive interference. Okay, so let's look at the key formulas. All right, there's just two of them. The key idea is knowing when to use them. So I'm going to draw a little table here. Okay, this will be the last thing we do, and we'll wrap this up. All right, so the table's going to look something like this. And so we're going to have a case here. This is going to be 0 or 2 reflective phase changes. So I'm just going to write that like so. Two phase, call them shifts. Okay, and this is the film thickness. Here I'm simply identifying that film thickness, m, can be an integer, and it can refer to 0, 1, 2, and so on. So 0, 1, 2, 3, right? Any integer, including 0. Okay, and then over here would be the case of one phase change. Okay, because you can have a case where there's no phase changes, where every time it's lower, you go from higher to lower to lower. That'd be no phase change at all. Or you could have a case like I drew above, where there's 2 phase changes because you went from lower to higher to higher. But then what about the case where there's only 1? Well, that would be from lower to higher back to lower. Okay, and so then the formulas correspond to that, and it basically looks like this: is that in the case of 0 or 2 phase changes, this formula right here refers to constructive interference. But that very same formula would be the correct formula to use for destructive interference if we only have a single phase change, because of the relative indices of refraction of the 3 materials, the first, second, and third, right? The air, the film, and then the material, or the liquid, the film, and then the material. Okay, so this would be destructive interference. And then just to make sure I label something in the formula, what is that T? Well, that T refers to the thickness. Okay, it's not time, but it's T for thickness. Okay, N again is the integer. It's double the thickness in order to get the destructive interference. That's because we need to be able to fit it's double the thickness because you've got a wave coming in, right? You've got a certain number of wavelengths that come in, and then you've got a certain number of wavelengths that come out, right? That's why it's double. In, out. Okay? All right, but then the next formula would be the correct formula to use if we were talking about destructive interference for 0 or 2 phase changes. Or constructive interference for just 1 phase change. Okay, so in the next video, you'll see kind of how we put that